Welcome to Radiology Artificial Intelligence Bits and Bytes. I'm Pedro Stasiaki. Landmark detection cardiac MRI by using a convolutional neural network. Cardiac MRI, otherwise known as CMR, is a mainstream modality for imaging the cardiovascular system. You can look at fibrosis, edema, and iron tissue compositions. You can also look at myocardial perfusion. Manual analysis of cardiac MRI takes from 9 to 19 minutes, and automated analyses could help decrease time. For automated analysis of cardiac MRI, landmark location is very important. The purpose of this study was to develop a convolutional neural network, or CNN, solution for landmark detection in cardiac MRI. This was a retrospective study performed in 2 hospitals in London, England. Inclusion criteria were all consecutive patients from December 2017 to March 2020, with holdout patients from May 2020 to July 2020. The ground truth was manual labeling by 2 readers. The first reader had 9 years of experience in cardiac MRI research and 3 years of experience of deep learning. This reader labeled all of the images. The second reader had 3 years of cardiac MRI clinical reporting and labeled only part of the data set. Models were tested on cardiac CNA images, late gadolinium enhancement, LGE images, and T1 maps. This is an example on short axis CNA images. The main landmarks were the anterior right ventricular insertion point, the posterior right ventricular insertion point, and the left ventricular cavity. On 2-chamber view, the anterior point, the inferior point, and apex were the landmarks. On 3-chamber view, the anteroseptal point, the infralateral point, and the apex were the landmarks. And on 4-chamber view, the infraseptal and the anterolateral points, in addition to the apex, were the landmarks. Training set included 34,089 images from 2,329 patients. 90% were used for training and 10% for validation. In the test set, 7,723 images from 531 consecutive patients were utilized. For model development, the landmark detection problem was handled with a heat map, where each landmark was convolved with a Gaussian kernel and converted into a spatial probability map or a heat map. To train the network, we used an entropy Bayes loss and the shape loss computed with the soft Dias ratio. The final loss was a combination of both processes. The architecture utilized was similar to a UNet, and the input of the model was a 2D image. The majority of images were CNA images, 86%. So the authors used a fine-tuning strategy by using transfer learning to train the models for late gadolinium enhancement and T1 mapping. For AI model evaluation, the authors looked at detection success rate, computed as a percentage of samples with landmarks correctly detected, and also they used Euclidean distance between landmarks and labels. So here are the results. For CNA images, the detection rate ranged from 96.6 to 100%. For LGE, it ranged from 97.6 to 99.5, and for T1 mapping, it was of 98.7%. Here you can see the landmark detection in the 2-chamber, 3-chamber, and 4-chamber CNA views, computed with Euclidean distance. As you can see, the distance is around 2 to 4 millimeters. These are the same measurements for the LGE, 2-chamber, 3-chamber, and 4-chamber. As you can see, the Euclidean distance ranged from 2.1 to 3.4 millimeters. Here we can see the same information for CNA, LGE, and T1 mapping for detection in the short axis views. The Euclidean distance ranged from around 1.5 to 3.5 millimeters. Here are examples of model performance on the short axis CNA view. Here are examples in the 2-chamber, 3-chamber, and 4-chamber views. Here are examples in the late gadolinium enhancement 2-chamber, 3-chamber, 4-chamber, and short axis views. And here are examples in the T1 mapping sequences. This is an example of what the Euclidean distance looks like. So strengths of this paper include 3 CMR imaging applications were tested with this novel strategy for landmark detection utilizing heat maps. Limitations include single reader label the entirety of data sets, with the second reader only labeling a few of those data. The data were from a single MRI vendor, and not all imaging sequences were performed across both institutions, which decreases generalizability across hospitals. The potentials of this study are to decrease time to segment cardiac MRI images and to automate cardiac MRI imaging segmentation in the future. So in conclusion, a CNN was developed for landmark detection on both long and short axis CMR images acquired with CNA, LGE, and T1 mapping sequences. The accuracy of CNN was comparable with the inter-reader variation.